Let's find the pH of a 0.35 molar solution of benzoic acid. It's a weak acid, and we're given the acid dissociation constant Ka of 6.3 times 10 to the negative 5. So we can express this dissociation of benzoic acid, a weak acid, as Ha reaching an equilibrium with the production of hydrogen ions and its conjugate base. We can set up an ICE table where I stands for the initial concentration, C stands for the change in concentration, and E stands for the concentration at equilibrium. These are the values we need, so we can plug them into our equilibrium expression. In order to get those values, we're going to need some information, and we're given the initial concentration is 0.35 moles per liter. Before this dissociates, there are no products. We're going to represent the change in concentration of the products as X, and because of the mole ratios, these are all 1:1:1 mole ratios. The change in the concentration of the conjugate base is also X, and the change, because it's using the reactants to make the products, the change in the concentration of the reactant, the weak acid, is also X, but negative. So the concentrations at equilibrium will just be the initial concentration plus the change, and that will give you the concentration at equilibrium. For both the hydrogen ion concentration and the conjugate base, the concentrations will be X at equilibrium, and the concentration of a weak acid will be 0.35 minus X. Now we can plug these values into our equilibrium expression. And we're given 6.3 times 10 to the negative 5. Ka, which is 6.3 times 10 to the negative 5, is equal to the concentrations of the products raised to their molar coefficient, which is all 1, over the concentrations of the reactant. So if we plug those numbers in, we get X times X, right? That goes there, and that goes there. X times X, we'll just call that X squared. And on the bottom, we're going to get 0.35 minus X. Now, to avoid the quadratic equation, X is so much smaller than 0.35 that subtracting it is not going to make a difference. It's going to be negligible. This is going to be like several degrees past the precision we're given of 0.35. So I don't know right now, but it might be like 0.0000 something. And adding or subtracting that small quantity from 0.35 is not going to make a difference. Now, we do have to confirm that that's true afterwards. On our test, it'll always be within 5%. Now the top you can't ignore because that's all we have in the numerator, and you're squaring it, and you're not just subtracting. So we can disregard that. Cross multiply there, and we're going to get X squared is equal to 6.3 times 10 to the negative 5 times 0.35. Punch these numbers in our calculator, 0.004697, and so on. Well, that's not going to be our final answer because it's asking us for pH. We have the H plus concentration. We just take the negative log of all of that. That's what pH means. Our P means is just negative log. pH is equal to 2.33. I think there's 2 sig figs in our original, right? So there's 2 significant figures there, 2 significant figures there. So our answer needs to have 2 digits to the right of the decimal. So there's our final answer.